Hello, and thank you all for joining us in this, which is the sixth in our series of webinars and the first of 2014 that discusses LimitState products with a focus on their features and specific applications. My name is Tom Pritchard. I'm the host for today's event, and I'll be introducing our speaker and also rounding up at the end. Today's webinar is modelling retaining walls with LimitState GEO. And hopefully what it will do is provide you with an overview of how you can use LimitState GEO, which is our geotechnical stability analysis software, to rapidly determine the critical failure mechanism and margin of safety for various retaining wall type problems in things such as gravity walls, cantilever sheet pile walls, anchored and prop sheet pile walls. The webinar will run until approximately 10 AM UK time, so about an hour, and there'll be some time at the end for questions. These can be posted by the question functionality that's present in the interface that you should all have on your screens. If it's minimized itself, then there's a little sort of orangey coloured arrow that you can use to pop it out again. We'll try to answer as many questions as we can in the time available at the end, but this isn't always possible, so apologies in advance if we're unable to get to yours. As usual, we've got a mixed audience today. Some of you will be quite familiar with LimitState GEO and some of you will be new to it. If anyone has questions regarding the software that might require a long or considered answer, then please feel free to contact us outside of the webinar via info@limitstate.com, and we'll be very happy to answer these in some detail for you. So without further delay, our speaker today is Dr. Colin Smith, who's the LimitState GEO product manager, and I will now pass you over to him.
Many thanks for that introduction, Tom. Good morning to those of you in the European time zone, and good afternoon or evening to those of you joining us from elsewhere in the world. As mentioned by Tom, my aim today is to show you how LimitState GEO can be used to solve retaining wall problems, and as part of that we'll look at how it differs from other methods and how to model a number of specific scenarios. So to this end I'll be using a mixture of slides and the software to illustrate the key points. In terms of what we're going to look at today, we'll have a quick recap on classic analysis approaches, and then look at the LimitState GEO modeling, how we can use that to model a range of problems, and we'll look specifically at gravity walls, cantilever sheet pile walls, and anchored prop walls in this particular presentation. As this is a problem-specific webinar, I'll focus on how the software can be used to solve retaining wall problems, so I may therefore skip over some of the details of how to use the software in general, but hopefully the process should be clear. Now, for those of you who are new to this webinar series, I think it's quite useful to first give you a little bit of context to the company and the software. The University of Sheffield has been researching limit state analysis and design and the use of optimization in civil engineering for almost 2 decades now, and the company LimitState was spun out from the university in 2006 with the aim of making this research available to industry. Now, of course, industry users want not only powerful tools but ease of use and support, which is what LimitState aims to provide. Also, the company has sophisticated testing systems in place. That means every time the software is run, over 800 tests are automatically run to make sure, every time the software is changed, over 800 tests are automatically run to ensure the software does what it's supposed to do. Now, the company has 2 products at present: LimitState Ring for the analysis of masonry arch bridges, and LimitState GEO, which is the subject of today's presentation, and several more products in the pipeline. Now, just to set LimitState GEO in the context of currently available software, on the one hand, we have software based on conventional hand-type calculation approaches, such as the method of slices for slopes, and these do a pretty good job for standard problems. If you're dealing with much more complicated problems, then you may use finite element software, which can deal with pretty much any problem geometry and very complex soil behavior, but typically requires a lot more expertise to use. Filling a gap in the middle between those 2 types, we could say, is computational limit analysis, which is what LimitState GEO provides, an ability to analyze the ultimate limit state with the flexibility of geometry specification that you get with finite elements, but the ease of use of traditional methods. In a sense, all you need in terms of parameters are cohesion, friction, and self-weight of the soil, and you can deal with a wide range of problems. And this next slide just illustrates the sort of scope of the software. You can model footings, retaining walls, slopes, combined problems, and soil structure interaction problems. So anything you can pretty well draw, you can model. But today we're going to focus on retaining wall analysis. So just a very brief recap. If we look at standard textbooks and design codes, we see a broad consensus on the general principles of retaining wall analysis, and these are adapted for specific scenarios. So for hand calculations, typically we're using a limit equilibrium approach, which might be a Coulomb wedge analysis, and that's very useful where you've got a variable backfill geometry or non-uniform surface surcharge, but isn't quite so convenient if you want to try and work out pressure distributions on your retaining wall. Alternatively, we have the Rankine analysis, which is very convenient for working out pressure distributions, dealing with layered soils, but can be trickier to deal with variable backfill geometry or non-uniform surface surcharge. You have to look at various modification factors or equations to deal with those sorts of things. And additionally, it doesn't really give you a feel for the extent of the mechanism behind the wall that is generating that active pressure, or in front of a wall that's generating the passive pressure. LimitState GEO can model a wide range of problems and essentially deal with the limitations of either of those previous approaches. Essentially, you can regard it as a very sophisticated Coulomb wedge analysis, but it is essentially able to give you full pressure distributions as from a Rankine analysis. So we can model gravity walls, gabion walls, cantilever stem walls, sheet pile walls of various forms, anchored and propped. And we're going to look at that in a little bit later. But first, I think it's helpful for those of you not familiar with how LimitState GEO works, just to recap on that process. So the analysis that the software carries out uses a computational limit analysis technique called discontinuity layout optimization. And essentially that provides rigorous upper bound plasticity solutions and is a rapid and direct means of going straight to the collapse state, no need to iterate towards that collapse state. Came out of a 5-year EPSRC funded research project at Sheffield, and was the initial method was published in the Proceedings of the Royal Society in 2007. There have been a significant number of publications since then. But it's very neat in that it essentially the essence of the method can be summarized in 4 simple diagrams. So here we have a footing or a block of soil loaded on the surface with a rigid boundary to the left and to the base. Unlike finite elements, this method works using nodes. So we populate the domain with a series of nodes. We connect every node to every other node with a potential slip line, and then we use optimization to pick out of that set of slip lines the set that gives you the critical mechanism, which in this case is a fairly simple 2-block sliding mechanism. And we started off with 12 nodes, which will give us 12 times 11, 132 potential slip lines, and out of that we can find this mechanism. So clearly if we put more nodes into the problem, we get more potential slip lines and a much more sophisticated mechanism, or more detailed mechanism. And typically we might be using 1,000 nodes, so we get almost 1 million potential slip lines, and from that the software can pick out a critical collapse mechanism. Now the way it's formulated underneath all that, the optimization is a sort of key part to it. It turns out that it can be formulated to a simple linear optimization problem, which is easy to solve on modern PCs with modern linear optimizing software. We use a commercial package, MOSEC, which was developed, I think, primarily for the finance industry, but is capable of handling thousands or millions of variables. And what the software does is, having identified the critical layout of slip lines, it can then turn those back, if you like, into solid sliding blocks, which are then animated to help interpretation, as we can see here with this example of a gravity wall. But the key point here, and in terms of understanding the method, is really that connection between the number of nodes, the number of potential slip lines, and then the complexity of the mechanism that can then be identified. So the more nodes you put in, the more precise the solution you're going to get. Now, of course, you want to be sure that this method actually gives you good results, accurate results, comparable to what's in the literature derived by the methods. So as I said, we automatically run over 800 tests every time the software is modified. A number of these have been put up on the web, and you can look at those. So let's put a simple one up here of a smooth back retaining wall, looking at the passive pressure on a body of soil which is half submerged. And we have a benchmark of 25.75, which is a theoretical solution, and the software generated a result which was only 0.06% out from that. So there are a lot of other results there, and perhaps picking another aspect of verification, this is looking at active earth pressure on a gravity wall with either a smooth interface on the back of the wall or a fully rough interface. And the graph on the right, the red lines are the theoretical values from conventional theory, and the blue markers are the results from DLO or LimitState GEO, and they pretty well match all the way down. And we can do the same for passive pressures. Again, the red lines are the theory. These correspond to the values recommended in say Eurocode 7, and the blue markers are the DLO results. So they match very, very closely, and you can see that it's able to model the typical curved surface you will see in a classic textbook analysis of passive earth pressure. So we do get very close correlations with active and passive pressures derived for these types of problems, but we can go further than that with the software. So just to pick out some of the other features that the software can model in terms of retaining walls, sorts of things that are important to a range of problems. With a retaining wall, you can't see it in detail here, but it is possible to specify the interface property between the wall and the soil. Often we're going to model that as a lower strength than the soil itself, and that is straightforward to do. The software can model tension cracks. So in this particular setup, we've actually got a body of clay. This layer on the top is clay sitting on top of sand, so the wall just pulls away from that body of clay in this case. It's very straightforward to put in variable surface loads or variably distributed surface loads, and the software will deal with that. Also, it will deal with variable backfill geometry, whether you've got slopes or a mixture of slopes and horizontal zones. Straightforward to deal with layered soils, and also with water pressures here. So here's just modeled a simple half-submerged wall, but can model a wider range of water there. We're not going to look at detail. There isn't time in this webinar to look in detail at the water modeling, and that will be addressed in a later webinar. But the software can model inclined water tables, different water pressure regimes in different parts of the model, or you can import water pressure distributions from other software to model, for example, seepage type water pressure distributions. So we'll look now at our first example of gravity wall analysis. Just by way of introduction, look at sort of standard sort of things that we might want to do in this case. So conventionally with a gravity wall, you may be interested in assessing its stability against sliding, overturning, or a bearing capacity failure. And essentially what you're doing there in conventional analysis is a check of 3 failure modes out of an infinite number. The actual failure mode may be some combination of the above 3 or something else you haven't envisaged. Clearly you might also want to consider global collapse, which doesn't really involve the wall, but the failure mechanism effectively bypasses the wall. Software, there's no need to carry out these separate checks. You can find the critical mechanism, let the software find the critical mechanism which may be one of those three, or as I've said, a sort of mixture of those failure modes. So we'll look at that at the software, how we can use that to model that in a moment, but first I think it's useful to just look at what we mean by an ultimate limit state analysis. So here we're analyzing the wall at a state of collapse. And of course, anything we design, we assume we hope it's going to be inherently stable and quite far from its ultimate limit state. So to do an ultimate limit state analysis, we somehow have to drive the system to collapse by some means. So in the software, we have to find a way of making the system collapse. In reality, if you wanted a retaining wall to collapse, you'd have to go along and push it or reduce its length or damage it in some way. Now, driving the system to collapse in conventional limit equilibrium analysis, often that's done sort of implicitly. You may not notice directly that you're effectively driving the system to collapse by some ways. In a numerical analysis, such as LimitState GEO, you have to do this explicitly. So this brings us to the concept of an adequacy factor, what we call an adequacy factor in the software. So one way of getting a retaining wall to collapse is to say how much bigger does a load have to be to cause collapse, or by what factor do we have to multiply that load to cause collapse. And we call that an adequacy factor on load, and that can be applied to surface loads or to soil self-weight. So we could apply that factor to the weight of the soil behind the wall. Alternatively, we can say how much smaller does the strength of the soil have to be to cause collapse, or by what factor F does this soil strength need to be reduced. And that would be an adequacy factor on strength. And in both cases, if you get a number bigger than 1, then the system essentially is stable. If it's less than 1, then the system is unstable. And it's important that if you're going to apply this to a load, you should pick an unfavorable load in the system. Now, in general, that adequacy factor will correspond to a global factor of safety, either on load or on strength. If you've already applied partial factors, such as, for example, using the Eurocode approach, then this becomes what we might call an over-design factor. And if you've already applied Eurocode factors, then for optimal design, you're looking for this adequacy factor to be equal to 1. Okay, well, that's enough sort of background. Let's look at the software and a demonstration of gravity wall analysis. So when you fire up the software, this is what you get in terms of the screen, and I shall bring up a gravity wall model that I've prepared previously. So just to look at the layout of the software, what we have a set of buttons on the left which primarily control how we can draw or modify the geometry. Along the top we have buttons controlling the solution and the display. Key on the right hand side is this property editor, which gives us the properties of anything we click on. So it's very sort of mouse driven. If I click on this object here, its properties appear in this property editor. That's a solid and it has certain properties in it, and it also has a geometry, and the geometry is displayed there. If I click on this wall, its properties are appeared up here and the geometry appears down here. So just to look at that, this body of soil behind the wall, I've clicked on that. There's an entry here which says there is one material assigned to it, and that's called soil A. And if I expand that, I can see that soil A has a C' value of 0, a phi dash of 38. It also has an undrained strength defined for it. And in the software, you can switch between using undrained and drained properties quite straightforwardly in a number of ways. One way is to just set this setting. This says always drained, so actually in this case it will always use the drained properties and never use the undrained. But you can change that to a different setting. And we have a weight of 18. That's 18 above the water table, and also in this case we've just for simplicity put 18 below. So that's essentially we've got a frictional soil of angle of friction of 38 degrees behind the wall. The wall itself, if I click on that, is made of a rigid material, so that essentially will not deform, but has a particular weight to it. And also you'll see that on the interfaces we have a different colored material. If I click on that, this is a boundary, and it's got a material called the wall soil interface. So actually we're modeling a reduced angle of friction of 25 on this interface, whereas the soil itself has 38. And the same for the base here. We have another material called the base interface, and that has the same angle of friction. These materials are all available in what we call a Material Explorer on the left, so we can find the same material, soil A, get its properties in the property editor. So anything you click on, its properties appear in the editor, and you can modify those. And we can model cohesion, friction, and also linear variation of cohesion with depth using these settings here. In terms of analyzing it, we have two possible modes. We can look at a factor load or a factor strength, so basically obtaining an adequacy factor in those contexts. A factor load, what we've done is we're going to say that let's apply it to this. So to do that, we set this thing called adequacy to true, and that just tells the software find the multiplier on the self-weight of that soil to give us collapse. So I'll just solve that problem. You can see the nodes there. We're using a fairly low number of nodes in this problem just for speed. Quickly identifies essentially a single Coulomb wedge. The wall is sliding there, and this number here is what we have to multiply down at the bottom left is what we have to multiply the soil self-weight by to cause collapse. So we've got a margin of safety about 1.5 on the weight of the soil. You'll see in the animation this wall is moving sideways, also moving upwards. That's due to modeling the friction on the base of the wall in plastic analysis. Friction is modeled as dilation, so in the animation you actually see that manifesting as dilation, but essentially it gives you the same effect for friction in most cases that we're looking at. I can switch to factor strength mode. That takes slightly longer as it has to iterate to a solution, but that will find the factor on strength required to cause collapse. That will tell us what our margin of safety is in that case. So it should get there fairly soon. So it's telling me that I got a factor of 1.14 on strength, and clearly the factor on strength is not going to be the same numerically as a factor on load. So here we've got a 14% margin on our strength before we're going to get collapse. Now we can employ partial factors in the analysis. We have a facility called the Scenario Manager, which allows you to apply different factors to different load types and different material properties. You can define your own, but the software has some Eurocode factors built in. I'll just look at Design Approach 1 Combination 2, which essentially factors down material strengths, 1.25 on frictional material, 1.4 on undrained, and essentially leaves the loading unfactored unless you've got a variable unfavorable load. So if we run that analysis using say factor load again, we get the diagnostic pops up, and this is quite useful just to give you some information about the problem you're modeling and just to help you check that you've set everything that's required. But it's saying we're applying partial factors, but we haven't actually told the program what loading is favorable or unfavorable or neutral. In this case, it doesn't really matter because all the loads that in this particular problem are going to be factored by 1, but we can set those separately using the property editor. So I've done a factor load analysis, and now I've got an adequacy factor on the load of 0.76. So that says you've got to multiply the weight of the soil by 0.76 to get collapse, which means that the system as currently specified is unstable with those partial factors applied. And that's what we'd expect, given the numbers we'd seen before. We're actually factoring the soil strength down too far to give us a stable design as originally specified. And we get the same result if we did a factor strength calculation. Initially we found we were 14% over strength, but design approach 1 combination 2 reduces the strength by 25%, so we would expect to find ourselves at about 0.9. A factor of 0.9 on there is about 25% lower than the 1.14. So we can do all our analyses in that way. Just for simplicity, I will revert back to a unit partial factor, and just for speed, we'll revert back to factor load. We can employ more nodes. The more nodes, sorry, I clicked the wrong button there. The more nodes we put in the problem, the higher the accuracy. But again, just for demonstration and interactive working, we'll work with what we call a coarse nodal distribution of 250 nodes. But clearly when you come up with a final design, you'd be wanting to put in more nodes to get a more accurate answer. So in this particular analysis, we've seen essentially a sliding failure. For this particular wall, overturning is quite unlikely, but we can model that. I'm just going to have to modify the geometry to get us something which will fail. So what I will do is make the back of the wall vertical. So I'm going to, well, let's do this. I can drag and drop the geometry. So picking that point there, I can move it along roughly where I want, or I can use a property editor here, a geometry editor here, to exactly set the geometry. Now you can draw the geometry using the on-screen tools, or you can import geometry from, say, a DXF file if you've got that already drawn for convenience. To make this thing fail by overturning, I'm going to have to make it a lot taller, so it's going to look very intuitively unstable like that. And the final thing I need to do is the interface at the bottom here. It models a frictional interface, and as a general rule, it's if we also add a no tension cutoff material, and I can just drag and drop that material onto the interface that I want, and I'm going to say add here, so that gives me a combination of a no tension cutoff and the interface material, and that allows the interfaces to come apart as you might get if you've got rotation about the toe. So I then solve that problem. I get an adequacy factor of around about 0.77, which shows that it isn't stable in its current state, and I get a toppling failure. We can see the gap forming here. Now I'll get toppling failure because the material model down here is a rigid material, so it's like modeling on rock. I should just point out that if I click on this object here, I can actually see distributions of stresses down the back of the wall, which are looking pretty much like Rankine earth pressures, except right at the bottom where there's a little increase in pressure due to the kinematics of the deformation. Now, that kind of illustrates toppling, but more often we're more likely to get a kind of bearing or eccentrically loaded bearing failure on the base of the wall. So if I just revert the geometry back to where we were originally, we'll replace that base material here, which, as I said, effectively represents rock, and we'll put a soft clay in there, and then we solve that. The software realizes there's effectively eccentric loading on that wall, and then we're going to get sliding but a little bit of toppling or a combined failure. Now you'll see down here we've got sort of eccentric mechanism, bearing failure mechanism, and the mechanism is actually intersecting the boundary. Unless that's a real boundary, then that's not going to give us an accurate result. We should extend the boundary so the mechanism does not intersect with the boundary. So I'll just move that back. Also, if there's a lot of deformation going in here, fairly complicated, then we would want to put more nodes. So I can click on that block, and we actually have a setting called baseline nodal spacing. So this sets a relative spacing of the nodes compared to any other area. So I'm going to change this to 0.25. And if we click, for example, on this zone, we see a spacing of 1. So that means that in the base zone, we're going to have the nodes spaced 4 times closer than in this zone. And we solve that. But then, we're not getting the mechanism intersecting the boundary now at the bottom, and it's modeling that better because it's able to use more slip lines. Haven't actually changed the answer that much. In terms of adequacy factor, it's gone down from 0.77 to 0.75, but there we're able to get the combined failure. So that's pretty much all I want to say about gravity walls. If you really want to check independently sliding, bearing, and overturning, you can force these mechanisms and check actions and resistances specific to that mechanism, but that's beyond the scope of this webinar. But do get in touch afterwards if you want further information on this. So I'm going to jump back to the PowerPoint now, if it's going to come back. There we go. And just before we go on to cantilever walls, just say a little bit about remind ourselves of some of the principles of ultimate limit state analysis. The software employs a rigid plastic model within a limit analysis framework to generate these ULS solutions. So essentially, you have to be careful in modeling brittle materials, and this is something that's well known using classic limit equilibrium approaches. So if you've got a shear stress, shear strain response of a material, may have a peak strength or it may not, then you need to be careful if you've got a peak strength, and the simplest option is to use a critical state strength. So for the bottom curve, we can just take the modeling strength we'd model as its peak strength, but for the upper curve, we'd take this ultimate or critical state strength rather than the peak strength. That's the safest option. Otherwise, you need to think a little bit carefully about how much strength is being mobilized in the problem. Okay, we'll move on to cantilever sheet power walls. Now, conventionally, if you do a limit equilibrium analysis of a cantilever wall, you probably assume Rankine earth pressure distributions. You assume the wall is going to rotate about a point near the base of the wall, and you're going to look at moment and horizontal equilibrium. And you can simplify the stress distribution below the wall with an equivalent force. Various ways of making that hand calculation easier. Essentially, what we're interested in is probably how long does that wall have to be to give us stability, and we'd also be interested in bending moments. So we'll look at the software and how we might model that. There we go. Okay, so here we've got a cantilever wall, and it's essentially surrounded by a loose sand with an angle of friction of 30, and we have a surcharge behind the wall. We're going to use a factor load analysis, so we're basically asking the software how much heavier does this surface load have to be to cause collapse, and we've set that surcharge to a load of 5 kilonewtons per meter squared, and we've set adequacy to true, so we're asking the software what do we have to multiply this value of 5 by to get collapse. So we get kind of 2 wedges, which we might expect, the sort of shape we expect for active pressures behind, passive pressures in front of the wall. And we find that actually that surface surcharge is slightly too high. It needs to be multiplied by 0.86 to give us actual stability. I've modeled this wall as a rigid block. If I actually click on the block, as before, I can see the pressure distribution. So what you can see here is essentially an active earth pressure distribution down the wall, and then suddenly it flips right at the base to effectively a passive pressure. So the point of rotation is right down here near the bottom of the wall. And likewise on the other side, we've got passive pressures, and then right at the bottom, the rate of increase drops as we revert to something closer to an active pressure. Of course, it doesn't really revert suddenly to simple active, simple passive pressure distribution. Things are a little bit more complicated, as you can see from the shape of the mechanism. Now we can change the length of the wall to try and get if we want the design to be exactly optimal to get an adequacy of 1, we can change that value. I might change that to, say, 0.4. So increase it slightly. Because we've almost got an optimal design. Most of the loading on the wall is from the self-weight of the soil rather than that surface surcharge, so it's going to be quite sensitive to that surface surcharge. So here we've now got an adequacy slightly above 1, so we know that we were pretty well around the right length of wall for that particular case. Pick up that model. If we want to model and get bending moments, we can use what's called an engineered element in the software. Now, an engineered element is a one-dimensional object which can transmit tension, bending, and shear stress within itself. And if I click on this wall here, we can see the material properties, and what we have is what's called right engineered element and left. So the right and left are the properties on the interface on the right-hand side and the left-hand side of the one-dimensional engineered element, and the engineered element itself is representing a sheet pile wall in this case. And engineered elements can be used to model soil reinforcement, so they have some other properties, but when we're modeling a sheet pile wall, we can set what are called the pull-out and lateral factors, essentially to infinity. 1 times 10 to the 30 is big enough. And primarily what we're interested in, if we're interested in bending of the wall, is its plastic moment of resistance. So the software can model a retaining wall and model plastic failure of that wall if we wish. So that's essentially what it's doing, but at the moment we've got a moderately high moment of resistance there, and it's just going to model a rigid wall all the way down with different properties on the sides of the wall. And if we look at what's on the right-hand side of the wall, what we see is we've got a frictionless interface. So that means we're modeling a perfectly smooth wall, and we've got tension cut off in case we had a tension crack. We are modeling sand here, so we aren't going to get any tension cracks, but if we'd been modeling clay, the software would be able to pick that up. So if I click Solve, we get a very nice sort of active and passive wedges, and the software actually is able to look at the forces on the wall and put together a bending moment distribution here. So we see the peak bending moment distribution down here gives you a peak bending moment of around about 25 at the base, so well below the 150 that we'd specified for the wall. But if you want to look at plastic failure of the wall, we can reduce that. So if I reduce that plastic moment of resistance to, say, 15, which is below that 25 that the analysis told us, then the software will actually find a different mechanism of failure where in fact the wall is going to fail by bending, and we get a sort of shallower failure. So you can put in a bending strength and see what will happen at the ultimate limit state. So that is very quickly a summary of the cantilever wall analysis. I'll just shut that down and jump back to the presentation. And just again to reiterate some of the issues that are present in all limit analysis or limit equilibrium analysis. We're using a rigid plastic model here, so we're assuming full soil strengths are mobilized simultaneously at failure, both passive and active. But in practice, certainly at working loads, they may be mobilized different. So as we kind of know for conventional limiter equilibrium analysis, serviceability limit state bending moment distributions and prop loads may be larger than predicted by the ULS model. Depends on the type of wall we're modeling, and there is guidance in the literature on appropriate use of ULS-derived bending moment distributions. Isn't time to talk about that in the webinar, but it's exactly the same principles as textbook examples on limit equilibrium analysis of returning walls. Okay, well, we're going to finish off by looking at propped and anchored sheet pile walls. So in a prop wall analysis, typically, well, what we want to know is how do we model the prop, how do we get the prop load out at ULS, and what are the pressure distributions here. You can see the mechanisms look quite different to a cantilever wall because we're getting rotation about the prop. We don't get that classic active wedge on the right-hand side. And then for anchored walls, how do we model the anchor and the anchor tendon in this case? What's the load in the anchor tendon? Does the anchor interact with the wall? Those are the sort of issues we might be interested in. So we'll have a look at those. So we'll jump back to the software. And what I'll do is we'll go back to that original cantilever wall analysis and actually put a prop in. So we can do this in various ways. Simplest way is just to draw in a rigid block somewhere along the wall. So I just draw a prop in as a rectangle. So I've drawn that very roughly. I shall just tidy up that geometry. So we've put in a block there. It's currently empty, so I'm going to make it just out of a rigid material. So this is going to be part of a prop, and I shall put a fixed boundary at this edge so that that prop is leaning against something solid, so it's unmoving. Now, if we want the wall to actually pivot freely about the prop, then what we want to do is make sure the interface of the prop has a no tension value on it. So we're now looking at the left-hand side, and it has a tension cutoff, which means essentially that the wall can lift off the prop and just rotate about the top or bottom corner freely. So that would model a totally free to rotate prop wall interface. And we're about 1 meter down from the top. So if I then solve that, I get a different failure mechanism as I had before. The wall should rotate about that prop. So if I zoom in, I think it's a little hard to see, but it's essentially hinging about the bottom corner of the prop, and we get a different pressure distribution as we'd expect. If you want to get the prop load, I can just click on this prop. Anything I click on, I can see force diagrams on that. So the force here at the end is telling me what the normal stress is on that boundary. So it's saying it's around about 1100 kilonewtons per meter squared. I know that's 0.3 meters high, so I can multiply those together to give me a force per unit length, and that's the predicted prop load at ultimate limit state. If I know what the prop capacity is, then I can actually put that in using a tension cutoff material. So if I duplicate this material, actually I'll do it this way. If I create a new material, I use what we call the cutoff material. And this, instead of allowing us to define strength of material in terms of shear strength, it says it actually puts limits on the normal stresses, the tensile and compressive stresses. So it says limiting tensile stress, limiting compressive stress. So what I'm going to put in here is a value roughly half the value we saw up here for that prop in terms of the stress. So basically it will fail at a load or a stress of 550. And I'll give it a suitable different color. Put that in, and you'll see that that has appeared here as a material. And I can put, yes, I can add that to this boundary here. And now that boundary, if the compressive stress goes above 550, this will actually fail and slide. So when I solve that problem, the software will find a different failure mode, slightly different failure mode, which involves or allows that prop to give way if that's going to be optimal in terms of the collapse mechanism. And you can see the prop is actually moving here past its boundary. And we get a different distribution, a slightly different mechanism, and a sort of combined sliding and rotational failure here. So that is a way of actually putting in the prop load. But of course, in many cases, the prop load or prop strength, props are going to show a sort of brittle response, peak response, which then might go down. So you do, again, need to be careful about how that is specified. I'll just revert that change and remove that material. The final thing just to point out in this analysis is what's going on with the wall at the top here. If you're modeling a truly rigid prop, the software is going to model a rigid plastic response. So if you're rotating about this point on the prop, then the top of the wall is actually moving into the soil. So the software will essentially model a passive type pressure distribution there because the wall is moving to the soil as we expect, and below the wall is moving away from the soil on the right hand side. Now in conventional limit equilibrium analysis, you just tend to model that as an active pressure and not worry about it. If it's a small length, it doesn't really matter. If it's a larger length, it may start to have an effect. And if that genuinely happens, then that is probably the right thing to model. However, because there are some compliant, the prop will be slightly compliant, etc., you may wish to address that. One way is to perhaps assume that the pressure here is smaller, and what you can do as a way of reducing the effect of this upper part of the boundary is to put in a sheet pile wall, and this just shows how we can link different sheet pile wall materials. If I duplicate that material, I've got to get a copy of a sheet pile wall, and I'm going to call this upper sheet pile wall. And what I'm going to do is put in a reduced bending strength there. So what I'm going to say is actually I think the earth pressures up here, perhaps we're not going to get full passive pressures, we're not going to get active pressures, maybe we'll get a lateral earth pressure coefficient of 1. I can work out quite easily what roughly what the bending moment down here would be for that to give me a lateral earth pressure of 1. And actually turns out in this case, because I'm a meter down with a unit weight of 14, it's a half 1 squared times 14, which is 7. If I put that in and then replace that up there, then what will happen is this upper sheet pile will be tied into the lower one, but it will actually happily bend at a stress of 7 kPa. That's larger than would give you active failure, but smaller than passive. And what happens then is that upper bit of the wall stays vertical, essentially, while the bottom part of the wall rotates. So up here, this part of the wall is actually it's rotating slightly, but if you put it in that sort of value, then you're basically taking the influence of that out from the analysis, which, as I said, in many cases it doesn't really matter if the prop's quite near the top of the wall, but can be something to think about. Okay, that's propped wall. We'll just very quickly look at an anchored sheet pile wall. So here I've modeled sheet pile wall. This is, again, has an engineered element modeling the wall with a certain bending strength, and we've got on the sides interface materials with particularly specified angle of friction. It's joined by an anchor tendon to effectively a Deadman anchor, and if I analyze that, in this particular case, it's been set up so that the anchor itself and the wall are just about going to fail simultaneously. So we get two mechanisms, and the wall rotates about the anchor point. Now, this particular problem, just the things to bring out, is that the anchor tendon itself, if I click on that, all we want that to do is to transmit tensile force, and we don't want it to interact with the soil. So that's set with an engineered element that has these pull-out and lateral factors set to 0. That effectively means it doesn't interact with the soil at all. It can just transmit tensile force. The key issue when modeling that is that when you join engineered elements to other engineered elements, at the joint, the software will pick the weakest material for failure. So if I join this 0 strength or low strength tendon, so I normally give that tendon a low bending strength, I should have pointed that out. We have a low moment of resistance. If I joined that straight to the wall, it would actually introduce at that point a hinge of 0 strength, and the wall would just fail at that. So what you have to do is just put in a short linking piece made of the same material as the wall, and that then takes a joint just behind the wall, so the wall can stay fully integral along its depth without any reduction of strength, and it's only at this point that the bending strength of the material reduces to 0. And the same again over here where we joined the anchor, we've got a short linking piece. So that's just one little tip on how looking at that. The other, just to finally finish, just nice to show this model in terms of the interaction of the anchor and the wall. We know that the anchor has to go a certain distance behind the wall so it doesn't interact. The previous analysis showed that those mechanisms weren't interacting, but I can pull that anchor closer to the wall, and we can see that the interaction is actually modeled. So I'm just selecting that anchor, and I'm going to click a button ortho here, which just means that anything I drag will move horizontally or vertically. And I'm going to pull that closer to the wall, move it a little bit further. So now intuitively you look at that and think that's really a bit too close to the wall. And if I solve that, our suspicions are confirmed, and what we get is a sliding failure essentially, and a much reduced stability. So just neatly illustrates how software can actually pick up interaction between different components of a wall system. Okay, I think that pretty well wraps up the demonstrations. We'll just wrap up with a summary. So hopefully I've shown you that in LimitState GEO we're using limit analysis. It's very similar principles and mechanics as conventional limit equilibrium methods, and we can adopt all this sort of framework around that, but we can handle very complex geometries and kinematics and interactions. We don't have to consider different failure modes. The software will automatically pick out the critical mechanism. It's very straightforward to handle layered soils, non-uniform surface loading, tension cracks, etc. And as I've said, it will automatically search all the possible failure modes every time you solve. Hopefully, as I've been using the software, you can see that it's very interactive, solves quickly, so you can use it to answer what-if type questions, change the geometry, look at the strength of soil, what happens if I do this. So you get a much better feel for the problem, you can see the shape of the mechanism, and you can solve essentially any ULS problem type. So there's no need to put in idealizations or correction factors to try and modify a standard solution to a non-standard geometry, and no need to use a different bit of software for a slope, for retaining walls, etc. So that wraps up the presentation. At this stage, we move to questions. So happy to invite questions. Sorry, just take a little while to pick out the questions from the system. All right. I'm just reading through the questions, trying to digest. Some of these are going to take rather a long while to answer. Some are easier. Okay. Got a question about, for gravity and cantilever walls, can we get the eccentricity and load distribution on the base of the wall? So for gravity walls, you can click on the wall itself and let me just... So I go back and put you can get the pressure distribution on the base of the wall, but that's going to depend very much on the material that you have on the base of the wall. So often get that question, can we work out the distribution, because you want to then show that it's stable, but actually the software is already doing that for you. It's already deciding whether that distribution under the wall, so here's a distribution under the wall in this case, is sufficient to cause failure in the soil. So if you want to get those values out, you can do, but really one should ideally be thinking of the software as doing the whole process for you. But obviously for checking purposes, you may want to look at that kind of distribution and see if it corresponds to, or how it relates to your conventional analysis, where essentially you're trying to break the problem up into two parts, doing a sort of moment equilibrium on the wall, estimating what the pressures are on the base, and then deciding whether those would actually cause instability on the soil underneath. So I hope that's answered that question. Yeah, for cantilever wall, retaining walls, will we get the forces and moments in the structural elements? Yes, so I think we showed that with the cantilever wall. Certainly when using engineered elements, if you solve that problem and click on it, you can get the ULS bending moments. I've got a question about modeling of friction. So plastic analysis, friction is modeled as dilation. That means that, yeah, if you're familiar with plastic analysis, the normality is imposed in the analysis. The analysis is a rigorous plastic analysis. Generally, when you have friction model as dilation, if you have very confined problems, that can cause a problem. So if the soil is very, very confined, the dilation can cause kind of locking. For problems where there's significant freedom, as in this problem on the screen now, generally we're getting results which are close to conventional analysis, so the dilation effect doesn't have a significant influence. Also, question about that cohesionless materials do not automatically include no tension. They do actually include no tension. It wasn't necessary to put a no tension interface onto the boundary where you're just retaining a friction-only material. As soon as that material has any cohesion to it, then you need to put a no tension condition on if you want to model tension cracks. So just as a kind of rule of thumb, if you always put a no tension material in, you're always covered and you won't forget. But yeah, in principle, you don't need to do that for a frictional material. Yeah, question about serviceability limit state. This is ultimate limit state software. Unfortunately, the ease of use you get out of it in terms of only having to put in cohesion and friction mean obviously you can't get a free lunch. You can get very flexible ultimate limit state modeling, but serviceability limit state is more difficult. There are various ways in the literature, people looking at how you can adapt or interpret ultimate limit state distributions to give you an estimate of serviceability limit state bending moment distributions. So concepts like mobilized strength and so on can be useful there, but the software does not do explicit elastic analysis. It's all ultimate limit state plastic analysis. There's a question about, are there webinar recordings, other information available to inform colleagues about how this analysis method works? Well, we have recordings of previous webinars, and a recording of this webinar will be put up on the web so that you can access that. And there are application notes and technical notes on the LimitState website which go into the details of some analysis methods, and those are being added to periodically, so there will be more and more information about those specific items. There are also some research papers in the literature which address some of these points in addition. Question about 3D version. We'd love to have a 3D version out. The theory has been established and demonstrated, but 3D problems take a lot longer to solve than 2D problems, so we're primarily looking at how we can get that sped up so it would then work in a useful time period. So that unfortunately is a little way off. Question about stiffness of the sheet pile wall. Again, we're not modeling, it's plastic analysis, so we're not modeling any elastic deformation or elastic response, so we're unable, the software won't, stiffness is kind of meaningless, so essentially what you're putting in, the only control over bending is over plastic moment of resistance, so we can model plastic failure of the wall together with plastic failure of the soil, but it's not modeling elastic response, so there's no stiffness response in there. So essentially it's going to give you a very good check on ultimate limit state. There are, for certain wall types, there are standard ways of interpreting the ultimate limit state response to help guide you in the serviceability limit state, but if serviceability is going to be critical in some cases, then you're going to need to use an additional analysis approach. But in this case, you could then use the software to check the ultimate limit state and also to some extent calibrate that serviceability limit state analysis. Okay, I think that looks like all the questions that I can see on my list here. Apologies if we've omitted anybody, but we're slightly over time there. So what I'm going to do now is hand back to my colleague Tom just to wrap up the presentation. So thank you very much for listening, and I hope that has been useful to you. So I'll now hand over to Tom.
Thanks, Colin, and like Colin says, thanks everybody for listening. We're now quite near to the end of the webinar. I hope you found it informative. Perhaps you learned some stuff that you didn't realise before about the software. As mentioned at the start, if the webinar's prompted any questions that we haven't answered for you already, then please feel free to get in touch via telephone or email us on support@limitstate.com, and we'll be happy to speak to you about it. For those of you who aren't current users of LimitState GEO, we'll try and get in touch with you over the next few days to get some feedback and find out if you have any further questions and see whether you think the software might be useful for you. As hinted at by Colin, if you'd like to watch the webinar again, or if you think you might know somebody who would be interested to see it, there will be a recording available later today, and a link will go out once it's available online. Also, please look out for our other webinars dealing with LimitState GEO, which we'll be sending out event notifications for in advance, and they're also posted on our website at www.limitState.com/events/webinars, and you can also see them through the events tab on the front page of our website. So there'll be some more coming up later in the year. So finally, I'd like to say thank you to everybody for listening, and hope that you can join us again for one of the future sessions. Goodbye.